Okay, so for FRQ number 6, we have a block of mass m and attached to one end of the string, and the string is wrapped over a pulley that has a radius of lowercase r and a moment of inertia of I. On the other end of the string, the other end of the string is wrapped around a hollow sphere that has a mass of m and a radius of capital M and a radius of capital R. So for part A, we are asked to find the speed of the object after this object has fallen 80 centimeters downwards after being released from rest. Okay, so first of all, I want to designate that T1, or this tension, T1 will be the tension of this rope closest to the small object right here, and T2 will be the tension of this rope closest to the hollow sphere. Okay, so let T1 be the tension of part of rope that is close to small object, and let T2 be the tension of rope part of the rope, that is close to the sphere. Okay, so we are also given that the radius of the sphere is 10 centimeters, and right away I'm going to convert that to meters, so that's going to be equal to 0.1 meter. The radius of the pulley is given to be 5 centimeters, so that is 0.05 meters. Okay, so part A, again, we were asked to find the speed. So speed after the system has moved 80 centimeters for the 80 centimeters. So to do this, we need to find the acceleration of the system. And to find the acceleration of the system, we need to first use Newton's to define the tensions. So looking at the object, the small object, the total force on the object is going to be equal to mass times acceleration. So looking at the object, there's the force of gravity and tension. So it's just Fg minus T1, as I've already designated in the beginning, and that's going to be equal to mass times acceleration. So Fgm is just mg minus T1 is equal to ma. Isolate for T1, I get T1 is equal to mg minus ma. Okay, so to define the other tension, I'm gonna have to use torque, and I have to look at this the sphere in this case. So total torque on the sphere is going to be equal to the total force that is perpendicular to the sphere times r, and that's going to be equal to the moment of inertia of the sphere times the angular acceleration of the sphere. So this turns into, for the total force on a sphere is just T2, and then you times that by R, and the moment of inertia of the sphere has a coefficient of 2/3, and it's mr squared, and the angular acceleration of the sphere is just basically the acceleration of the system divided by the radius of the sphere. And so now we just have to isolate for T2. So if we multiply the R over, we get, when we divide the R over, all the R is going to cancel out. So we get T2 is equal to 2/3 ma. Okay, so now that we have our two tensions defined, we're gonna look at the pulley now. So the total torque on the pulley is gonna be equal to the total force that's perpendicular to the pulley times its moment of arm, r, just lowercase r, and that's gonna be equal to the moment of inertia of the pulley times its angular acceleration. So the total force that's perpendicular to the pulley would be the two tensions, and this tension is going to be bigger, so it's going to come first. So it's going to be T1 minus T2 times R is equal to the moment of inertia pulley, and again the angular acceleration of the pulley is equal to the acceleration of the system divided by the radius of the pulley. So it's just A divided by R. Okay, so we've already defined our tensions up here, here, and here. So we just have to plug it in into the equation. So mg minus ma, that's T1, minus 2/3 ma, that's T2. Everything's multiplied by R, and that's equal to I pulley times A over R. Now I'm going to distribute all the R's to everything in the parentheses. So mgr minus mar minus 2/3 capital MAR is equal to I pulley AR. Okay, so what I'm gonna do now is I add this and this over here. So I'm gonna be left with mgr is equal to I pulley. Wait, no. I'm gonna keep. No, actually, yeah. So I add everything over. So I pulley times A over R plus add this over, so you get MAR plus add this over 2/3 MAR, capital MAR. So now I can factor out an A from all of these since they all have an A right here. So I'm gonna have A is equal to A I pulley divided by R plus MR plus 2/3 capital MR, and that's equal to MGR. So now I just need to isolate for A, which is what I'm trying to find. So I divide all of this thing over. So it's gonna be, so A is gonna be equal to MGR divided by this whole thing. So I pulley over R plus MR plus 2/3 MR. And plugging our numbers. So 0.5 times, okay, I forgot to tell you, mass of the block is 0.5. The radius of the pulley is, I've already defined up here, 0.05. The moment of inertia of the pulley is given to be 3 times 10 to the negative 3. Again, R is 0.05 plus 0.5 right here times R is 0.05 plus 2/3 capital M is 5 kilograms, and lowercase r is just 0.05. So plugging all this in the calculator, you get 0.9735 meters per second squared as your acceleration of the system and the block. So having this, we can set up the kinematic equation Vf squared minus Vi squared is equal to 2a and changing this the distance traveled. So this is going to be 0 because initially the system's at rest. So we want to find how much speed it gains after traveling 80 centimeters, and 80 centimeters is 0.8 meters. We need to make that conversion first. Okay, so what we're trying to find is Vf. So we plug in our numbers. Vf squared is equal to 2. Acceleration we just found is 0.9735 times distance traveled 0.8. So we square all of that. Square root all of that. So Vf is going to be equal to square root of all of this. 735 times 0.8. And that's going to be equal to 1.248 meters per second. So that's our velocity. Our velocity after the block has moved 80 centimeters downwards. Okay, part B, we are asked to find the time it takes for the block to descend 80 centimeters. So let me see. All we have to do is use this kinematic equation now. So delta y is equal to Vi y times t plus 1/2 at squared, ayt squared. So we move 0.8 centimeters downwards. Meters downwards. Our VIY was initially 0, so nothing. And our acceleration we found to be 0.9735. Sorry about that. 9735 and times t squared. So we want to find time. So if we isolating for time, we multiply 2 over and divide by 0.9735 and square root everything. So it's gonna look like this. Times 2 and then divide by 0.9735 and square root everything. There you go. And you get 1.282 seconds as the time. Okay, part C, we are asked to determine the sphere shell's rotational kinetic energy after 80 centimeters of the core has been unwounded. So for this one, we're gonna have to set up this equation. Ke rot of the sphere is gonna be equal to 1/2 times the moment inertia of the sphere times the angular acceleration of the sphere. The angular velocity of the sphere squared. So I sphere is 2/3 mr squared. And it's important to note that W sphere, the angular acceleration of the sphere is the final velocity that we found right here, over the radius of the sphere. So plugging the numbers in, you get 1.248 over radius of the sphere is 0.1 and that's equal to 12.48 rads per second. So we plug this in our equation right here. So 1/2, 2/3, big M is 5, R is 0.1 squared, and then omega is 12.48 then squared. And plugging this into the calculator, we get 2.596 joules. Okay. Part D, we want to find what fraction of the total energy has been transferred to the pulley. Okay, so first we want to find what energy the pulley has at the end, and then we're gonna have to divide that by the total to find the fraction, the total kinetic energy. Okay, so your KE rod pulley, which is the total kinetic energy of the pulley, it's gonna be equal to 1/2 I pulley times omega final of the pulley squared. Okay, so omega of the pulley is essentially just VF divided by the radius of the pulley. So it's just 1.248 divided by 0.05, which is the radius of the pulley, and you get 24.96 rads per second. So we plug this into the equation, and we get 1/2 times so radius, the coefficient of pulley is the I pulley is given to be 3 times 10 to the -3. Omega of the pulley we found to be 24.96. and we square that, and so from this we get 0.9345 joules. So that is how much kinetic energy the pulley has after being unwound. After the system has moved 80 centimeters. So now we have to find the total kinetic energy and the total energy, and the total energy is essentially just equal to the total energy final is essentially just equal to the total energy initial, because energy is conserved, and the total energy initial is just the potential energy of the object that is hanging. So it is just mghi. So the block is 0.5, gravity 9.8. Initially, the block is 80 centimeters up, so 0.8. And so our total energy becomes 3.92 joules when we put this in the calculator. So now that we have the kinetic energy of the pulley and our total energy of the system, we just have to divide them. So the fraction of energy transferred to pulley is equal to the KE rod of pulley over total energy. So energy total. So that's just 0.9345 divided by 3.92 joules. And if we simplify this and put the denominator as 1, we get 0.238 over 1.